Okay, this is problem 3, part B of section 2.3. We've already done problem 3, part A. Here U is the linear transformation from P2 of R to R3 given by U of the polynomial A plus BX plus CX squared is equal to the vector A plus B, C, A minus B. Okay, so we're given beta is the standard basis of P2R, which is 1x x squared, and gamma is the standard basis of R3, which we've written in row form 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so in this problem we let h of x be the polynomial 3 minus 2x plus x squared, and we're asked to compute the coordinate vector of h of x relative to beta and u of h of x relative to gamma. Okay, and in the last part of the problem, we're asked to use the matrix of the transformation U relative to beta and gamma that we calculated from part A and theorem 2.4 to verify the result. Okay. Okay, so again, h of x is equal to 3 minus 2x plus x squared, and we want to calculate the coordinate vector of h of x relative to beta. This is quite easy because we can see that our polynomial is 3 times 1 minus 2 times x plus 1 times x squared, and that's the coordinate vector, 3 minus 2, 1. Okay, so next we work out u of h of x, and we'll use the formula up above. We're given that u of a plus bx plus cx squared is this vector, so we'll use this with a equals 3, b equals minus 2, and c equals 1. Okay, so our vector is a plus b is 1, c is 1, and a minus b is 5. So that means that the coordinate vector of h of x relative to the standard basis, gamma is quite easy. It's just the vector 1, 1, 5, but remember we must write it in column form. Okay, so we've calculated the two things, and now we're asked to use the matrix from part A and theorem 2.14 to verify this result. Okay. Okay, so in part A, we found that the matrix of U relative to the bases beta and gamma was a certain 3 by 3 matrix. Okay, which I've forgotten what it is for a moment, so let me just look it up. Boy, what did I do with it? Okay, just going back to my notes from before. Right, so in part A we found that matrix was, first column was 1, 0, 1, second column was 1, 0, minus 1, and 0, 1, 0. Okay, so that's 3 by 3 matrix. Okay, now we're supposed to use theorem 2.14. So by theorem 2.14, we have an equation that looks like this. U of h of x On the left-hand side are the matrix of U and the coordinate vector of h of x. Now over here we have the coordinate vector relative to beta. The matrix here goes from respect to bases beta and gamma, and the coordinate vector over here is relative to gamma. Okay, so this is equal to the matrix 1, 1, 0, 0, 0, 1, 1, minus 1, 0, times the vector we worked out already, which was 3 minus 2, 1. So we need to multiply this 3 by 3 matrix by this column vector. One way to calculate that is to notice this is a linear combination of the columns. So we write down the columns. And the linear combination is just 3 times the first guy, minus 2 times the second, plus 1 times the third. And that means our vector is 1, 1, 5. Okay, so that means that the coordinate vector of u of h of x relative to gamma is 1, 1, 5. So therefore, okay, yeah, we're done because my mistake. In part, earlier we calculated the coordinate vector of u of h of x with respect to gamma is 1, 1, 5, and that agrees with what we've got here. Okay, so this verifies our result.